So to do this example, the first thing that you need to do is find where this curve is above and below the x-axis. And so absent any context, so you should start doing that. So for example, if all we had was find the area under this curve, we would need to know what the graph looks like to know that it never goes under the x-axis. So really when you're asked to find an area under a curve or between two curves, it's really helpful to start with a graph so you know if there's any problem with the curve becoming positive or negative. So for this one, we need to look at a graph of this and where does the graph cross the x-axis. In order to do that, we can look at the form of the function, say this is a parabola. I can graph it by finding the x-intercepts, and I can find the x-intercepts by factoring. So this is x minus 1, x minus 2. So the x-intercepts are x equals 1, x equals 2. This is a parabola facing up. So this kind of graphical analysis you need to be able to do quickly and efficiently. You can get, for example, right away the y-intercept is 2. You can get a fairly accurate graph. The x-intercepts are 1 and 2, which are really the only important things here. So there's 1, there's 2. And we have a parabola facing up because the leading coefficient is positive. So I know my graph looks like this. So the important thing that I observe is that I have a part of the graph that is above the x-axis, a part of the graph that is below the x-axis, and the breakpoint where they split is x equals 1. So that means that what I'm going to need to do is break this integral up as, I'll start by saying that the area equals the integral from 0 to 1 of x squared minus 3x plus 2 dx. All right, that's the positive part. And then for the negative part, this area is going to be negative, so what I'm going to do is put a negative in front of my integral, resulting in a positive. So I'm going to do integral from 1 to 2 of x squared minus 3x plus 2 dx. So every integral takes a dx at the end. That's really part of the notation. It's a remnant of the delta x, but it's considered part of the notation. All right, so the positive area minus the negative area. And of course, if you had another positive area, then you put plus positive. And if you had two negative areas, you would make them both negative. So you could have any combination of these positive and negative areas. All right, so now let's work out what it is. So we're going to do the antiderivative of x squared minus 3x plus 2 is x cubed over 3 minus 3x squared over 2 plus 2x. We're doing that bit from 0 to 1. And then I have a minus. There's like a lot of minus signs floating around. You got to really keep your eye on the detail, not always my own personal forte. So sometimes, doing these by hand is a challenge. But you need to get used to doing them by hand because they could definitely give you an integral like this on a non-calculator problem. Also, it's just good skills to develop. So this says evaluated from 1 to 2. All right, now I just plug and chug. So I like to sort of notate this with some additional parentheses. I'm putting in the 1, so I'm going to have 1/3 minus 3/2 plus 2, and then close the parentheses, and then a minus sign for the fundamental theorem of calculus. And then even though when I put in the 0, I get 0 for everything, I like to write that, and that just sort of notationally indicates to me that I did consider that 0, that I didn't just forget about it. So, that's optional, but it's a good way to organize your work. So now I'm going to plug in the 2 for the top. So I'm going to have 8/3 minus 12 over 2 plus 4, and then minus for the fundamental theorem. And then I'm plugging in the 1, and I'm not going to get 0 this time. I'm going to get 1/3 plus, sorry, see, this is where I'm thinking of distributing this negative, but we don't do that yet. Minus 12 over 2, I could just call it 6 right away, but I didn't, so there, and then plus 2. All right, and then close that off. So then another good thing to do next is let's just distribute all these minus signs because I got dozens of minus signs. Let's try to get those signs looking right. So if I distribute out the minus signs and also reduce the 12 over 2, looks like I'm going to have 1/3 minus 3/2 plus 2, and then for this one I'm going to have minus 8/3 plus 6, right, distributing the negative, minus 4. And then be really careful with this one because negative is positive, so plus 1/3. Negative is minus 6. Something seems weird here. Something is weird. 8/3, 12/2, 4. 1/3 Oh, this should be 3 over 2, right? Because when I plugged in the 1, I knew something was weird because this number looked too big. When I plugged in the 1, see what I mean about attention to detail? When I plugged in the 1, I should have 3 over 2 there. Yeah, everything else looks right. Okay, so then I have plus 1/3. Okay, and then minus 3 over 2, so minus 3 over 2. And then minus plus 2, so that's plus 2. All right. Then another thing you can do is sort of look for things that group and things that can cancel. So for example, I can cancel. Well, I can't necessarily cancel things. Maybe I can cancel some things. Yeah, I don't know what I did there. But I can go like this. So that's weird. Oh, I see. So 1/3 plus 1/3 minus 8/3 would give me negative 6/3, right? So that's -2. I like having my notes here. I can't even understand my own notes. And then I have negative 3/2 minus 3/2. That gives me negative 6/2, which is -3. All right. And then I have plus 2, plus 2, plus 2, so plus 2, plus 2, plus 2, and lo and behold, the total area is 1. You're going to think the area of everything is 1, but it's not. It's just I didn't even plan this, so I just said, let's do something that goes above and below, and I made up this function. This area is exactly 1. I found that so surprising when I first did this that I went and graphed it and said, does that look plausible? So here's the graph, and let's try to get this glare off it. Here's the graph, and yeah, you can sort of see like here's the 1 by 1 square right there. So it kind of makes sense that this part plus this part could plausibly equal the entire square. But I think it's astounding, really, that if you take this weird parabolic part and this weird parabolic part, and you put them together with this weird parabolic part, it just exactly fills the square. It's kind of remarkable. You get a lot of interesting, remarkable results like that from these problems. I wanted to observe some other things about this before I close off this problem. Well, I guess this video is getting long, so I'll observe the other things in the next video.